So optimal control theory continued from Hoy's chapter 25. So now we're going to look at optimization problems involving discounting. Y naught is equal to y of t e to the power negative rho t is the discounted or present value of y of t. Here rho is the rate of return, which is a known constant over time. You see, when we multiply y of t with e to the power minus rho t, we are effectively dividing y with e to the power plus rho t. So whenever we divide something, we are discounting it or figuring out the present value of the quantity. In dynamic programming problems, time enters the objective function explicitly through the term e to the power minus rho t. See, over here we have t. If this is the only way the variable t enters the dynamic optimization problem, the system of differential equations, lambda dot and x dot, can be made autonomous. Now, why would we wish to make a system autonomous? It is because autonomous differential equations, where t is not an explicit variable, are easier to solve. Whereas non-autonomous differential equations, where t is explicit, for example, b of t, they are harder to solve. So we always prefer to have differential equations which are autonomous and can be solved in an easier fashion. Now recall the general form of the dynamic optimization problem. You want to maximize the functional between the lower limit of 0 and some upper time limit, capital T, of a function that has x of t, y of t, and t itself. Now x of t and y of t are both implicit functions of t, whereas here t stands on its own explicitly. Subject to boundary conditions, x dot is equal to g of x of t, y of t, and t. And the boundary condition x of 0 is equal to x naught, usually taken to be positive. Now look at the integrand f of xyt and look at the constraint g of xyt. Imagine that we could quote unquote take out t and get a capital F of xy and a capital G of xy multiplied by some function of t instead. So instead of t being inside the function, it is now outside the function, but multiplied with it. Homothetic functions have this property. If we are able to do so, right, take t out and multiply it by some function of t instead. So if we are able to do that, then we would be able to transform the non-autonomous equations into autonomous equations which are easier to solve. So let's look at an autonomous discounting optimization problem. Here we maximize j between 0 and capital T, capital F of xt, yt multiplied by e to the power negative rho t. Right, we are multiplying capital F by a function of t. So t enters this expression in an explicit fashion. Subject to x dot is equal to g of xt, yt, and x of 0 is equal to x naught. So the regular Hamiltonian for this problem is just h is equal to capital F of xy times e to the power negative rho t plus lambda g of xy. Maximization with respect to y occurs when, so we differentiate this with respect to y, partially differentiate this expression with respect to y and set it equal to 0. So when we do that, we get f sub y times e to the power minus rho t, which is a constant, plus lambda, again a constant, g sub y is equal to 0. Now we multiply both sides by e to the power plus rho t, and when we do that, then e to the power minus rho t times e to the power plus rho t is equal to e to the power 0, which is just 1. So you have f sub y when you plus times 1 plus lambda e to the power plus rho t g of y x of y equal to 0. G sub y, x of y equal to 0. So this is what you get when you multiply both sides by e to the power plus rho t. Solve this equation for y, right? So if we had algebraic forms, we could find out an expression for y in terms of x and lambda e to the power rho t. So suppose we could do it, and we would get y as a function phi of x and lambda e to the power rho t. Next, we need the differential equation for lambda. So lambda dot is equal to minus del h by del x, which is equal to minus e to the power minus rho t f sub x minus lambda g sub x. Check it, you will get this result. When we plug in y is equal to phi of x lambda e to the power rho t, we get lambda dot is equal to minus e to the power minus rho t f sub x of x and phi, right? So instead of y, we are writing this function phi minus lambda g sub x, x and phi. Once again, you multiply both sides by e to the power plus rho t. On the left-hand side, you get e to the power plus rho t times lambda dot. And this becomes 1 when you multiply it with e to the power plus rho t. You get negative f sub x, x phi, minus lambda times e to the power rho t, g sub x, x phi. We have this equation for lambda dot, right? So we have an equation for lambda dot. We have the second differential equation for x dot. Here we have it, x dot is equal to g of x of t and y of t. And the boundary conditions, x of 0 is equal to x naught. And we can use the transversality condition, lambda of capital T is equal to 0. Capital T is, again, the upper limit of the integral. Note that the differential equations lambda dot and x dot are still not autonomous, right? Because T is still explicit. You see, T is inside this phi. Phi has a lambda e to the power rho t. This is an explicit function of T, right? Here we have another e to the power phi t. This is an explicit function of T, right? So since T is still explicit, lambda dot and x dot are not autonomous. In order to make them autonomous, we need to define a new variable. Mu of t is equal to lambda of t to the power rho t. So mu of t is just a new co-state variable. We make an adjustment to our original co-state variable, lambda, by multiplying it with e to the power plus rho t. Now, if mu is equal to lambda e to the power plus rho t, then if you differentiate both sides, you get mu dot is equal to rho lambda e to the power rho t plus lambda dot e to the power rho t, which is equal to rho mu plus lambda dot e to the power rho t, right? Because mu is equal to this thing, and we replace rho times lambda e to the power rho t with mu. So we have rho mu. Now recall y is equal to phi of x lambda e to the power rho t, and e to the power rho t times lambda dot is equal to minus f sub x of x and phi minus lambda e to the power rho t g sub x of x and phi. So if you can rearrange this, you will get lambda dot e to the power rho t is equal to minus f sub x, x, and phi of x lambda e to the power. So we are writing phi completely over here, minus lambda e to the power rho t g sub x, x phi of x lambda e to the power rho t. So all we are doing is we're just completely writing down phi dot explicitly. Now we can substitute for lambda e to the power rho t and lambda dot e to the power rho t in the above expression. Firstly, notice that lambda dot e to the power rho t is equal to mu dot minus rho mu, which permits us to write mu dot is equal to rho mu. So when I take rho mu to the right-hand side, I get plus rho mu, minus f sub x, x, phi of x mu, right? So I can replace lambda e to the power rho t with mu, minus mu, g sub x, x phi x of mu. We also have the differential equation governing x, x dot is equal to g, x phi of x and mu. So previously we had a pair of differential equations in x dot and lambda dot, where t was explicit, Now we have an equivalent pair, mu dot and x dot, both of which are functions of time, but in which t does not appear explicitly, right? T appears implicitly in these expressions. We have transformed a pair of non-autonomous equations into a pair of autonomous equations.